thank you so much. Thank you for organizers, Roland and Paula, and for the honor to open this meeting. So for the next 25 minutes, I'll try to entertain you and talk about neural networks, and specifically for this session, kind of kickstart things with maybe a little bit intro about the neural network potential. And before I run out of time, those are members of my lab who actually did the work. It's historical Mellon Institute in Pittsburgh. A lot of collaboration with group of Purdue, University of Florida, Los Alamos, funding from the Office of Null Research and National Science Foundation. And we're also part of the new NSF Institute in the States, Center for Computer-Assisted Synthesis. A bunch of organic chemists, analytical chemists, computational chemists, and computer scientists come together with kind of a dream to digitize and make organic chemistry modern kind of data-driven science. Well, if you think about the problem in computational chemistry, and depending where you stand, you might pose with this dilemma, right? If I have my system of million atoms, you're kind of stuck to use classical force fields, or if you really want to get the correct or precise answer, you want to solve the electronic Schrödinger equation. And kind of to think about, that's our time-independent Schrödinger equation, and I think the impact of the machine learning was here, because if you look for this equation as a data scientist, you realize, oh, that's a supervised regression problem, right? So my ground state energy would be magic function f from the molecular coordinates, and this is why we are here, because all of us pursue to find this magic function f. In my lab, we fun of the neural networks. So we take molecules in, pass them through neural network, get your energy. And the beauty of neural network, they're fully differentiable, right? So we backpropagate, and you can get gradients. Now you can do geometry minimization. You can do molecular dynamics. You can backpropagate twice. Now you have second derivative. You have a hash matrix. And you can compute properties, spectra, things like that. Now, and kind of to put this into context, right, if you think about computational scaling of various methods versus some kind of metric of accuracy, again, if you're looking to simulate proteins, you're kind of stuck here, force field realm, which are typically linear scaling. It's not that force fields are bad, but the uncertainty can be very high, right? You're not sure if the force fields are transferable from one system to another. So to reduce this uncertainty, you have to climb this ladder, right? Maybe you can go on semi-empirical tight binding methods, density functional theory, conventional couple cluster theory. And in my realm of organic molecules, a couple cluster theory, what's called the gold standard, right? So you get 1 kcal per mole accuracy, but you pay the price of 7 scaling for the conventional couple cluster theory. But if you really want to do exact answer, this is you have a full CI complete basis set if you want to get an exact answer, but it's not practical for any realistic system. So the spoiler alert, right? That's why we're all here. We want to find those methods that combine favorable scaling and approach the accuracy of the reference quantum mechanical theory. In many cases, we use density functional theory. Now, and things we've been doing for past 5-6 years. So ANI, deep neural network framework, was the first example of transferable neural network-based force field. We train it once, and then you use it as this black box method. You plug it in your favorite simulation engine and do the simulation for small organic molecules. Again, been parameterized for mostly drug-like small organic molecules in a gas phase, and give you an accuracy about kcal or 2 from the DFT reference. Now, why it works, and it goes to all the way to our friend nearsightedness principle, chemical interactions. You've seen curves like that, hydrogen molecule, water dimer, right? At certain cutoff, you can truncate the interactions and ignore everything above the threshold. you can see there's a little star, which means there's a disclaimer, right? So it ignores long-range interactions, and for some systems, those are crucially important. So this approximation holds for certain classes of molecules and materials, and in practice, it works very well for organic molecules. And therefore, based on this principle, it goes all the way back to, seminal paper of Baer and Paparinella, idea of representing atoms inside the molecule as atomic environment. For any neural network, we use a different mathematical form. I call it Justin-Smith symmetry function by the name of the talented graduate student, Justin, who was a graduate student at that time, so he hates me for that, but I think he totally deserves the credit. And therefore, each atom inside your molecule characterized by this sphere and essentially this molecular neighborhood, and the total energy of the system would be sum of these atomic environments. Now, so ANI architecture is a feed-forward simple neural network. You take your Cartesian coordinates, transform in this symmetry function. You have the radial part and angular part, pass them through little neural network, get essentially this local fictitious energy, sum them up. This is E total, right? Very simple. Now, essentially, it makes a revolution in how we deal with the small molecules, and I'll not bore you with the technical details. There are a couple of papers, but essentially, it solves the problem of getting molecular geometries and accurate potential energy surface for small organic molecules. There are a few examples of kind of drug-like molecules that were traditionally very hard to describe for force fields. So you have a lot of sulfur, halogens. And if I take a couple of the hydrals, you see the comparison of this potential surface map from DFT and ANI. None of these molecules were specifically in the training data. And it gets you essentially 1 or 2 kcal per mole, and gets you very accurate description of the potential energy surface. The same with reaction thermochemistry can get you very accurate gas phase thermochemistry. And over the time, we extended the ecosystem. For example, it's a little convenience package we call After3D. It helps you to find the stable conformers, either the lowest or the ensemble of conformers starting from the small strings. So what it does, it can help you enumerate the tautomers, stereoisomers, and we build the essentially parallel geometry optimization engine that runs very fast on the GPUs, and it's a Python library or command line interface, and you can run essentially hundreds conformers, optimize 100 conformers per minute. Little application example, how it works. So if you get, DFT, calculate free energy of tautomerization for a particular bunch of different molecules from the database, and compute free energy, gas phase free energy tautomerization using standard, kind of rigid rotor approximation. Delta G ANI versus DFT, basically get very high correlation, mean absolute error 1.5 kcal per mole, and wide variety range of the energies. Now, the latest, what we kind of pushed this approach is to build essentially a reactive model, again using the same tools as an active learning. 1 year later, this preprint's still under review. So if you're interested to read the technical details, but essentially we use idea of nanoreactor from Todd Martinez, but instead of running ab initio molecular dynamics, we use a potential itself, and essentially train transferable reactive potentials that can work for CHNO chemistry. Again, in the paper, we applied to a bunch of different applications. And for example, things like carbon nucleation, oxidation of graphene, combustion, biofuels, things like that. And again, the potential been trained on small organic molecules. And if you now look back to this architecture, what it ignores, a couple of things. Long-range interaction, as I mentioned. And also our descriptor is purely geometrical. It doesn't take molecular charge and spin multiplicity. So our first step to improve that is augment that. Oh, and our preprint was also our fingerprint was also prescribed geometrical, prescribed mathematical form. Now our next generation of the methods, what we called atoms and molecules neural network, extended this approach that you start from molecular geometry, but also neural network learns those embeddings, what's called, essentially how atoms inside the molecules, and clearly we were inspired by Bader theory, where atoms described by the electron density, but here we get vectors that are learned and are consistent with their neighbors, and our means to pass long-range interaction, what's called the message passing, have our own flavor of this message passing interface, message passing neural network that get these updates and update to the vectors, and you compute local energy and then sum them up to the total energy. Again, published 2019. What allow us to do is improve the accuracy, but also now you can analyze those vectors and do a little heuristic interpretations, what the neural network learned a little bit about chemistry and so forth. So our latest things was to address this idea, how to encode spin and multiplicity. And again, until probably last year, there was no ML methods readily available that encode electronic degrees of freedom to that. And our idea was to augment neural network with external building block. So again, published in 2021, what's called the neural spin equilibration method, which essentially little data-driven block inside the neural network that assigned spin charges into the molecule. And if you look, for example, this the prototypical example, so it's a conjugated system with the electron withdrawing and donating group. So if you attach or detach electrons, what DFT tells you, this is highly non-local things, right? You see the spin density, so the spin charge goes as the spin waves, right? If you use just purely geometrical descriptor, predict the spin charges, neural network gets you absolutely wrong because it's all more or less the same, right? And using the NSC, you can get a closer answer. Now, which brings us to kind of the topic for AIMNet2 is all of these things together, right? We have message passing. Now we condition neural network to a total molecular charge or spin multiplicity. We have this neural spin equilibration block, which assigns spin charges or charges for closed systems, and we add more physics, right? In addition to local energy, there's no need to waste neurons to learn dispersion. You can just add it as is it D3 or TS method or MBD. So you have physics-based dispersion, and we have long-range electrostatics. Since we have charges, you can directly plug it into your favorite MD engine and compute with particle mass Ewald or whatever approaches. So you have three terms, sum them up, gets total energy. The preprint was posted, again, a couple of months ago, still under review. Which brings us to AIMNet2. So extended the ANI framework from 7 elements to 14. So now we parameterize essentially all non-metals, including silicon, boron, selenium, arsenic as you care, iodine, and so forth. Again, we sampled from different databases, and they paid the price of this transferability of data set of 20 million of molecules. So there's a sample from the training set. Now, how it works? It gets you very accurate energy and geometries. So I went to the CSD Cambridge crystal structure database to look for molecules with unusual bonding from these element organic molecules. Now, what you can see here is 2D structures and 3D. And those structures were so unusual that ChemDraw complains and get these errors, right? So you see halogen 6 coordinated with another halogen. You see fluorine and 2 arsenic. You see boron clusters with selenium, few phosphorus in the row. So what I get in this exercise, I took CSD geometry, I took the molecule itself and minimized with the potential. And this is, you see how good the correspondence of the crystal structure versus optimized. You see, preservation of the energies, with the exception of probably with this one torsion angles. Geometries are well represented. And again, here we make approximation that I minimize molecule in the gas phase and compare with the crystal structure. How it works with respect to total molecular charge. Now we can do molecules with arbitrary charges. It's terrible regression plots. So this is neutral molecules, plus, minus 1 and 2, and 3 and more charge. What is important is look how consistent RMSD errors across the range. So it works very well for neutral molecules, +1, +5, you name it. All across the board, accuracy is consistent for both charged and neutral molecules. Now, if you care about the benchmarks, works really well for torsion profiles. It gets to the accuracy of the semi-empirical methods like AIMNet2, which is also commercial closed source. Works very well on GMTK of the various subset, barrier heights, intermolecular interactions, you name it. I'll not bother you with steps. How we do in terms of the computational accuracy for a small molecule size? It's compare with the GFN-FF or xTB. On a GPU, it's probably 5 times faster than GFN-FF. On CPU, it's a few times faster than xTB itself. In a kind of a limit of the larger size, again, it's a linear scaling method. For example, a system for 20,000 atoms, you can get energy and forces with 0.2 seconds. And overall, again, for medium-sized molecules, you can optimize hundreds of conformers a second if you run on a GPU. So you can really provide you high throughput calculations for molecular energies. Now, what we work right now is to extend it and kind of attack the problem of localizing transition states and accelerate finding of different reactions. What so far we sampled mostly molecular geometries and non-equilibrium geometries around the minima. But making truly reactive potential that can localize transition states, find the ARC reaction coordinates, you need to sample not only around here, but also around transition states along the pathway and off the pathway, right? It's a much more complicated problem. So to that regard, what we've been doing is systematically investing into generating of the reactive data. So this example of collaboration with the group of Brett Savo at Purdue University, which we released this essentially largest data set of reactions. So it's about 150,000 distinct, kind of CHNO containing molecular reactions with reference transition states as a DFT, annotation of the reactants products, and corresponding pathways. Which brings us to what we work right now is to combine all of that together to sample geometries with the MD along the pathway, breaking different bonds, kind of make what we call the reaction AIMNet. It's not published yet, but let me show you a couple of examples, highlight how it works. If you look for classical Diels-Alder reactions, and we take the DFT as the reference data, look how accurately we can compute activation barriers, so this transition state energies, half kcal per mole. If I run ARC profiles, DFT versus neural network, essentially one on top of each other. You can hardly see the different transition states where you expected to see. And what is even more rewarding is that, how accurate geometries for the transition states with a very, very small RMSD. So that's example of one reactions. The same, for example, the click chemistry, the triazole reactions, more or less the same story. And we tested in several different important mechanisms of reaction, things like combustion, atomization, hydrogen transfer, so forth. If you don't see your favorite reactions, find me, and we hope to extend it. With that, what we also have the opportunity not only improve the method itself, but also the way how we can find reaction. So for example, things like Groenstein method or a non-elastic band. With neural network, what we can do, we can take advantage of that neural networks are notoriously parallel, and we can reformulate all of this algorithm as batched version. So instead of traditional sequential optimization of the images along the reaction path, what we can do, batch them and optimize multiple reactions at the same time. And one of my talented postdoc is currently developing a library, which will be shortly released, of all of these methods, as non-elastic band, Groenstein methods, essentially in the batch versions, where you can run hundreds of thousands of reactions in parallel just on a single GPU. And that would transform the way how we can find networks of the reactions and do high throughput reaction screening. Is that? Let me close. And again, all of our codes are on GitHub. We get plugins for ASC, bunch of popular packages, OpenMM, Amber, NumD, Tinker, Lamps. So AIMNet is here. Most of our reference data is also on the GitHub. With that, thank you very much, and looking forward for discussion and questions.
Thank you. How to turn it on. So thank you, Olexandr, for a very inspiring presentation. I'm sure there are a lot of questions in the audience.
Maybe shout.
Now it works. Now it seems to work. Yeah, let's
see if this works. So very, very impressive, and I've been looking forward to see these things done with different spin multiplicities. And you have gone one step towards where I would like to go. You started to do transition states. So the next thing will be, of course, conical intersections and excited states. Tell us, is this something that is at the end of the tunnel?
I'm a simple ground state person, but there are enough people who do this in this audience. So I'm very excited about that. Excited states and non-adiabatic dynamics.
Hello, thanks for a great talk. I had a question specifically on the batch NAP stuff. So am I right to understand that you're not just batching different types of molecules over the similar reaction, but you're also looking at multiple reaction barriers, so that you've got a start point and end point, and there might be multiple barriers in between, and you're just batching NAP sequentially together to find all the transition states involved?
That we have not done.
Okay.
That can be done. At this point,
when you say batch, you mean batching, similar reaction, a single path?
Yes. So you take reactant and products. They may not belong to the same reaction. It's just, you start, first and last image, right? And for example, NAB, do linear interpolation. So they may belong to different classes of reaction, but this is one step.
So is it just a matter of deploying it in a batched way onto the GPU, or are you making those NAPs talk to each other in a certain way that...
So each path would be independent.
Okay.
We just batch them because of the very fast, tensor operations on a GPU. But in principle, you can be elaborate and combine multiple steps. At this point, we've done simple thing as just either Groenstein method or NAB, just doing the parallel calculus. But in principle, you can do multiple steps.
We have a question over here.
Great. Thank you again for the really interesting talk. So my question is about the reaction AIMNet. And here I'm curious to what extent you've explored the generalization capabilities of this model, because there's two that's quite interesting. So one is if you train on a subset of those reaction classes that you had there, and then see can your model generalize actually to completely unseen reaction classes. And then the second is if I'm guessing the training data is quite small, kind of molecules and kind of barriers corresponding to small molecules and reactions around those molecules. So how it would generalize to predicting barriers for much larger molecules where maybe we can't afford the same computational.
Great question. So first part, what we do in training, we use essentially combinatorial methods to do reaction without specific mechanism. And since we explore wildly, that kind of gives you this generalization. And then we test them on specific well-known reaction mechanisms that organic chemists care, right? So in the training data example, again, I apologize, I skip kind of technical, but happy to discuss. We didn't explore specifically Diels-Alder chemistry in the training, but it practice works very well. It's also a simple reaction. We sample small molecules, but also go into 40, 50, 60 atoms. So it explores some long range and kind of longer interactions. So it works well if that type of interaction was explored. It will not work if some kind of new phenomenon. So there's no magic here, right? So if you explore this type of interaction, it works, right? If you explore that particular bond breaking, right, that will work. If there is no, I don't know, sulfur iodine bond breaking, it will probably not extrapolate if it never seen iodine sulfur bond breaking. But in practice, again, it works quite well for wide variety. And here again, the types of, if you mentioned the type of reaction, what I show you, there's no like Suzuki coupling yet, right? Because we don't have, for example, palladium yet. There's no metal yet.
Right, thank you.
Okay. We have a question over here as well, please.
So thank you very much for the very impressive talk. I was wondering, have you tried calculating the potential energy surfaces of very large conjugated molecules?
Yes, we tried graphene, we tried diamond, clusters like that with polyenes. Geometries are well. We have not explored as things, in like phonons. So I don't know, but usually geometries, energies are decent.
So for example, if you have a longer and longer polyene, the bond length alternation changes.
Yes, that is well reproduced.
Wow, this is really impressive.
Maybe Pavla will talk about in his talk.
Please.
So thank you for the excellent talk. I had a question. So when you give the neural network the ability to produce charges as an intermediate that you're using in energies, in theory now you have the ability to compute a polarizability. I could put in a probe molecule like a lithium and I can see what happens to these charges. Have you assessed how the molecular polarizabilities of molecules compare to, say, the DFT computed polarizabilities?
Not yet. But the charges, what we've done a little bit, dipoles are very good, quadruples are very well, and multiples, but we have not done polarizability yet. Yeah. But I would imagine, if they would correlate as well.
We have Shell over there, up in the corner.
Up here.
Oh, yeah.
Thank you for a very nice talk. So I was thinking, you said the work was not published and so on, but could you comment maybe a bit if you do like architectural changes, or if it's just the training data?
Is the AIMNet2, the architecture, the last architecture I show, and it's mostly mostly in the reference training data that is needed to make this reactive potential.
Okay, it's quite amazing that it works so well. Thanks.
But again, those data sets the transferability comes at the price of very large data set, tens of millions of. So my carbon footprint is awful.
That was my question, actually. What is your carbon footprint of this potential?
I don't want even to calculate it.
We have a question here. Do we have the... Wait for the microphone so we can get it into the...
Throw it.
Hello. Yeah. So you partly answered my question already regarding, so I wanted to ask if you were going to look into metal catalyzed reactions, and you said that you haven't done that yet, but is this on the roadmap to look into Suzuki
Yes.
Hardwick?
Yes, so we do, spoiler. So palladium works very well. I have a student who started doing this. We have not done anything into more interesting metals, nickel, iron, and things like that. But again, fixed architecture, just matter of training data, and the palladium is easy.
But, so does this include the ligand as well?
Yes.
Okay.
Yes. Transition state reaction, you can find all the all the steps for the standard the palladium cross-coupling reaction.
Okay. Thank you.
Do we have any Roland here?
Roland?
Oops. That's the dangerous.
Now you see how hard work it is to be the chairman of the conference. You're using DFT.
Yes.
And you're reproducing DFT. But is that the preferred method for homolytic bond cleavage? Or are you going to sort of target other methods to really be able to describe chemistry where you form and break bonds?
Yes. So since we use DFT, all the errors are embedded, right? But what we've done a little bit is you can combine and use idea for things like transfer learning. You can start with DFT, and then, for example, for bond breaking, what we can do, use, whatever, for DLP-NO, couple cluster, whatever method. The problem is, if you want to do transferable, you need to run tens of thousands of these calculations. So this is not straightforward. So in principle, yes, it's just the problem of finding enough compute time to get there. But again, we use not the worst functional, so it's range-separated hybrid, omega B97, which gets you decent accurate. It's not perfect, but it gets you reasonable transition states. It gets reasonable BD, bond dissociation energies.
So do we have a final question? We have still some time. So I think this is a very good start of the conference. You inspired a lot of questions in the audience, which is good.
Nice talk again. I was wondering, in the reactive neural networks, did I understand well that you also want to do reactive force fields?
Yes. So the neural network has no topology, right? So the method itself is reactive by nature, right? You will get an incorrect, chemistry because it's not sampled, right? So making the potential reactive is just a matter of sampling the chemistry space that, bond breaking information.
So I understand the exploration during the training. I don't understand what the output would look like. What the reactive force field that it's outputting, how...
You can do reactive MD, right? You put your favorite simulation package, I don't know, LAMPS, but now you don't have a force field. So it can break bond. If you heat things up, you will cook reactions. So it will happen naturally. As ab initio MD, right? Or you can, with the latest, you can find transition states through standard methods.
Okay, so it's
and
not...
ARCs and all the things as you do normally. There's nothing special in it.
Maybe it's that I'm not that familiar with reactive force fields, but so it's not outputting force constants and
no,
like
exactly the same as you run quantum mechanics, right? You get energy forces, things like that. But then reactive in a sense that you can apply methods to find either localized transition states or run MD that will naturally describe, if reaction happens under this condition, it will show it.
Mm-hmm.
So with this, I think we should thank Olexandr once
Thank
again
you.
for a very excellent presentation. And at the same time,